let's roll. Weather lesson. So you all have gone, well, except Alexei, but in theory, he's actually very well educated. But every private pilot has gone through a weather um, topic on his private pilot. But the big difference in the weather for the private pilot is you're learning where you should not fly to. You see clouds, you don't go there. Like what kind of clouds? That may tell you something, but generally you just don't go there. Well, for instrument rating, that changes a lot. You go through the weather, but there are some kinds that you have to avoid, and the ones that you can't, you have to be able to deal with. So while we are talking about somewhat the same weather, it's at a whole different level. For today, I should be able to set the stage for what you expect, key weather phenomena, key items that you need to know. But there is no way in the world I can fit this in even several hours. There are three um, amazing resources that go deep into this topic, starting with somewhat of a surface level, the PHACs. Obviously, there is just enough about the weather to start asking some good questions. But the most education, the most learning that I've accomplished was in advisory circular, the 00-6B. It goes into a great level of details, and it's not as terribly large, just a few dozen pages, very readable. But FAA really did a great job of putting all the weather, IFR related weather in one place. So highly, highly recommend this. And then another handbook, this weather handbook, is another version of more pictures and easy to read, that is actually produced as a paper copy, which Advisory Circular is not. So take note, those three, especially that AC006B, that if you read that and get comfortable with all that's in there, you're probably 90% happy with your IFR weather knowledge. Okay, enough said on how scary this all is. Let's dive into a little bit of what the weather is. First of all, in my mock checkride as well, I was asked, well, how high is the area of this air that we fly in? How it's cold? What are the gases in it? And it's kind of knowledge that just nice to have. The part of the atmosphere that we fly in is called troposphere, and 78% of all the gases in that is nitrogen. It's like, and for me, first learning this a while back was kind of shocking. Like, what, really? We all say we need oxygen, but it's 80% nitrogen. Okay. Oxygen is only 21%. And by the way, this ratio doesn't change with altitude. Air becomes less dense, but the composition of gases is the same. Besides oxygen and nitrogen, everything else is just 1 or so percent, so very, very little of all other gases in the atmosphere. So that's what the atmosphere is. But again, the troposphere is where we fly. So there are 4 levels, from 0 to roughly 7 miles. That's the troposphere. That's where we live, breathe, fly mostly. Some planes can go higher into the tropopause, and very few would go in the stratosphere. They differ, those layers, why they're separated, they differ by how the temperature changes with altitude. And another thing is the troposphere height changes depending on the season, depending on temperatures, and jet stream has a lot to do with that. So again, just seeding you enough data to have this high level picture, but there is a lot of reading that would have to be done to be comfortable. And I honestly enjoyed that advisory circular. It was a good read too. Interesting. So within the atmosphere, we have the troposphere. That's where we fly. Now, Then we get to how the winds move. If and why the wind is even taking place. The whole reason is there's more solar energy that's absorbed by the equator, and as air heats up, it expands, rises, and then travels, and then cools down and settles at the poles. Now, if the Earth, like this picture is simplified, if Earth would be just a stable, not spinning, the air would simply move along the surface to the equator, rise up, and then um, float back to the poles, North Pole and South Pole, and that would be very predictable. Now, unfortunately, this is where it gets complicated. Probably by now you've heard about the Coriolis force. Because of the Earth movement, the air can't float in a straight path from equator to the poles and the way back. So it starts making those three distinct what is called patterns, cells, and those cells they move. They have dependency on the seasons of the year, and again, knowing and at least having a high level understanding of how this works would be awesome. But what you absolutely must be able to explain is the Coriolis force. The easy way to think about that is if you look at this picture down below, and I'll get my laser pointer here, and the Earth is rotating from, like, if you take a point on the Earth, it goes from right to left. If you throw a piece of air from the equator down to the pole, it will um, the Earth is spinning. If you take a parcel of air or a baseball or something and throw it real hard from equator down to the pole, it won't make it. It will change direction because it had higher velocity, because points on the equator are moving faster than points in the North Pole. The North Pole isn't moving at all. It's just spinning around its own axis. So same thing happens with the air. The air is being deflected by this Coriolis force, and it just starts making those cells, and that creates a lot of this weather fluctuations, or weather patterns. Now, um, going through all this makes my head spinning with Coriolis force, but again, I probably will be rereading that advisory circular myself, and I will keep sending you to do the same. That will be a good read. So those three pictures that goes on my slide, we went through the summary of, we have weather phenomena because we have uneven heating. There's more heat on the equator. Air tries to move. Because of the spinning Earth, we have cells, and then three distinct cells near equator, then mid latitude, and then at the pole are living their own little lives, and they're like self contained in there. That's in a high level um, what happening with the air movement in the troposphere. Yeah, that one was hard. Okay, on to a little easier part. So we talk about pressure, we fly using atmospheric pressure. There are some standards. When we say standard pressure, we have that we long time ago it was defined that a sea level pressure at a average level of the ocean, when the pressure is exactly 2992, that would be called a standard. In reality, it never is. It's either above or below. And so when we fly, we have to adjust altimeter often to make sure that we have a good reference on where the ground is using the altimeter. Now, the pressure decreases approximately 1 inch per 1,000 feet of altitude gain. That's another good number to remember. And so you could be getting a kind of quick little quizzes on, well, if you're like down below here, if your sea level pressure is 2992, what roughly pressure is at 3,000 feet? And then that's an easy math of just approximately 3 inch less of the pressure. Now the temperature, again, there are a couple rules of thumb that will help you to solve some quizzes at the written test as well as at the oral part. The standard temperature is a 15 degrees Celsius. The temperature decreases approximately 2 degrees per 1,000 foot of altitude gain. And that right there is your super easy way to figure out where is the freezing level. So just in a couple months, we'll be sitting here with some low clouds, hoping to do some IFR flying, but the temperature on the ground will be 8 degrees centigrade, which means the freezing level will probably be at 4,000 foot, not a whole lot of altitude to do any approaches. So that's one of the magic numbers to remember. There will be a couple more later on the slides. I'm not sure why I mixed them into the later slides, but we'll see. Now, a couple other weather items that you have to remember. The points of high and low pressure. And this, again, throws us back to the Coriolis force of understanding how this air moves around the points of high and low pressure. Well, first of all, what is the point of high pressure? That is when the air is literally pressing from above. The cold air is descending onto point on the ground, and that's creating that high pressure area. Now, when that happens, that air is colder and typically drier, so that typically brings a good weather. Now, this one is how I personally memorize this. This diagram, this picture is maybe a little misleading, but what you have to remember is the high pressure area, the air descends, so it's moving downward. And think of a regular screw. The way the screw would be screwing itself into the ground, it would rotate clockwise. So descending air rotates clockwise around the center of this point. And when it does so, descending, it goes clockwise and outward. That's something you'll definitely be asked to explain if you see high pressure areas and low pressure, what's happening with the air. Now, in this case, if you have two pressure areas like this, a high and a low, you can there you go. So what you can do is, you know that air is spinning around the high pressure area and goes outwards. For the low pressure areas, the air goes inward like this, and it rises. Again, low pressure areas is where the warm air got sucked upwards, and so the pressure is decreasing on the ground and all the moist air is going up. So in this case, the two pressure areas, the high pressure and the low pressure, being next to each other, will create the flow of the air from the higher to the lower pressure areas that would be connected along this line, so that it flows from the high pressure area outward to the low pressure area inward. High pressure area is when the air is pushing downwards, so we have the pressure, air has to escape somewhere, it does this clockwise and outward movement. And then the low pressure does opposite. And you combine them together and it makes sense. But of course, DP will make it more complicated than that. Okay, next topic, again, very high level, convective currents. There are a few, and we'll just hit on the couple key convective currents. So, for example, near the ocean, like right now, next several days past at least, we have all the cold air that's being sucked in from the ocean onto Tillamook, And the whole Tillamook area is IFR. As we're boiling here, the coastal range is preventing the air from reaching Portland, Hillsborough, and it warms up, it rises, and creates a lot of clouds. And that the circulation is just happening there because we have heat on the coastal range that heats up the moist air. And by the way, the moist air is lighter. That's one of the mind breakers. If you add water to the air, it becomes lighter. You just have to memorize that, I guess. So that warm, moist air is more prone to rising and creates a lot of clouds, beautiful clouds over Tillamook right now. At night, this will reverse. You'll have the colder air because of the ground is cooling faster than the ocean. Cold air will descend onto the shore and flow outward to the ocean where it will get heated up and rise. So those are the two probably most popular convective currents. Now, what this does to us, if you look at this picture, similar thing happens over the smaller bodies of water. The air is colder and likely sinking. If you are going over a darker, maybe paved areas, flying onto the lake, you're likely to have some downdraft. So as you fly, you start to, even on a smaller scale, you start to take those into account, and hopefully this will be helpful one day. But then there's obviously more to those convective currents. The worst, biggest convective currents happen when you have thunderstorms. Think of the same pictures here, a lot of moist air for some reason being pushed upwards. If the atmosphere is unstable, and definition of unstable is the air that's moving upwards is prone to acceleration versus deceleration, that's when we have thunderstorms. And those thunderstorms are so significant for aviation that we have convective segments that are significant meteorological events that are only dedicated to thunderstorms. But more about that later. Just trying to add some color that those convective currents, they seem very harmless when you just look at a little lake by a little parking lot, but they are the same in nature in what creates thunderstorms. A little more about the convective currents. In mountainous areas, there is a weird pattern that the air creates being blown over the mountain and then descending itself in a very turbulent way. That is why in Civil Air Patrol we have that mountain flying course. If you're flying around the mountains, you really have to be aware of what's happening and what to expect. Now, another topic that definitely comes up multiple times on the written, on the oral, came up on mine on the mock, and that was a difficult one. The microbursts. So think about those high pressure areas when the cold air descends. Well, under certain conditions, you can have a very concentrated burst of descending air. And what it does is when you approach that, for example, if that's on a takeoff, initially you'll have an increased headwind, which feels like almost a good thing to have because you have more airspeed. But then that changes in position 2 to a strong downdraft. And then in position 3 and 4, you have decreasing indicated airspeed with continuous downdraft. And climbing into a microburst will more than likely lead to a bad outcome because those microbursts can be up to a 6,000 feet per minute descent. So that's a pretty bad weather phenomenon. Again, that's one of the convective currents that are harmful to airplanes. Moving on, there's more. So when we have convective currents that are strong and they can be in a clear area and concentrated, that's what creates turbulence. Now, Let me distill this slide a little better. So I did mention the atmospheric stability as a term. That's one of the key foundational, I would say, mechanisms in the atmosphere that we have to understand, and we can tell if atmosphere is stable or not by looking at temperature aloft, for example. In short, this is what the atmospheric stability is. It's an ability of the atmosphere to resist vertical motion. If a force pushes a parcel of air upward, we have to think what happens next. It can either stop and pull itself down, that means atmosphere is stable, or under certain conditions, that vertical movement only becomes larger. So stable atmosphere makes that movement difficult, and then the air becomes stable, it moves less. If like last couple days were a good example, we had a lot of that smoke and bad visibility that is just sitting over the ground, not moving anywhere. We have that poor in-flight visibility exactly because the atmosphere was stable. On the bright side, it was very smooth, almost no turbulence, almost nothing, blown quite a lot. Now, unstable, that's a complete opposite. If you have a force like that maybe heated parking lot that was able to heat up a large amount of air, large enough that started moving upwards, and if that air is wet, moist, that parcel of air could be said to keep accelerating. And first of all, that leads to a turbulence because if airplane hits that thermal, glider people love them. They use them to gain altitude. But for us, fixed engine guys, fixed wing, yeah, fixed engine, single engine, fixed wing airplanes, that only means turbulence that we don't enjoy. On the bright side, better visibility, because when air is constantly moving like that, you are typically looking at a clearer air. So stable atmosphere, no turbulence, bad visibility, no thunderstorms. Unstable atmosphere, likely to get a thunderstorm if you have moisture, if you have lifting force, and watch out for those thermals. It can be bumpy. Okay, this may not be as exciting as those approach lessons. I get it, but thank you for listening through this with me. Couple more. I'll keep going until you guys drop off, or until 7 p.m. So I was literally asked by Sam Terrell, if you know the guy, what is adiabatic? So I had to make this slide. This is a term that's nice to understand, but before I even explain that, we have to remind us on a couple things. If you take a gas, oxygen or whatever, propane, or think of your favorite aerosol air freshener maybe. If the pressure inside the can decreases, because you let the gas out, it obviously expands because it comes out and it cools. That's why you feel really actually cold gas that's coming out of a can of any sort, any aerosol sprayer. You'll have that cold air feeling because that gas that's expanding, it cools itself down. Now, if you take this amount of gas and somehow will prevent heat exchange, that gas will not be absorbing heat from your environment, from your room, then that process of expansion will be called adiabatic. And that goes pretty deeply into science of defining how stable atmosphere and what to expect. For us, at least you have to be able to wave your hands around and explain what does it mean. And again, that moist air, yes, it is lighter. So if you have two air masses next to each other, one is moist and one is very dry, the dry air will settle down, the moist air will go on top, Next, since it's going on top, it will expand, and then it will cool itself down. And when it does, it will make a cloud, and that cloud will create rain and all other weather phenomena. So see how it's all connected. It's still, in my experience, one of the most complicated topics if you try to get this all correctly understood and then try to explain it. Yeah. Okay. So what else? Adiabatic lapse rate. Now, what it means? If a dry air is being lifted, if you take some if you have some form of keeping this air um, in some form of I want to say enclosure, but that would mean pressure. So somehow you have isolated this parcel of air, and you start rising this, you start lifting that in the atmosphere without heating it up or without cooling it down. This air will lose 3 degrees per 1,000 foot lifted, and that's a standard dry air. Notice how different that is with the moist air. The moist air can be cooling itself as little as 1.1 degrees per 1,000 foot. So remember when I told you the 2 degrees per 1,000 feet, that's the temperature change. So now imagine if we have a 10 degrees at the surface, and at 4,000 feet, this would cool down to a 2 degrees. So we're going from 10, cooling down to 2 degrees. But if you have a super moist air, like in Florida, that air being lifted from the surface, if something pushed that air up, will cool down only 4 degrees. So if that happens, then the moist air finds itself 4,000 feet in the air with only 4.4 degrees lost of the temperature. So instead of 10, now it's heating at 5.6, which means significantly warmer than 2 degrees standard temperature at that altitude. Next thing that happens, if that air is warmer than everything around that, it will keep rising. That's a good example of unstable atmosphere, and that's how the moist air plays into this by being lighter and having a lower adiabatic lapse rate. There. I need a beer, I think. Hopefully it still makes sense. I think it'll take me a few times to explain before it will make complete sense to me. But let's keep pushing. A few more. I promise to have it over by 7 p.m. So the pain stops at 7. Okay, so now I'm starting to repeat this a little bit, and there'll be a nice visual on the next slide, because this concept is pretty critical. This normal temperature lapse rate, the one that I mentioned, that is us getting in a Cessna, climbing 1,000 feet. We look outside, it's 2 degrees less. We climb 10,000 feet, it's 20 degrees less. Great. So right now it's 30 degrees outside. At 10,000 feet, it will be 10. Easy. That's your normal just temperature lapse rate. Don't confuse with that adiabatic lapse rate for the air.
I was going to ask you that.
Yeah, exactly. So that's different. Now, unless something takes this moist air and pushes it upward, it's not going to move itself. But that's where a little bit of a sidekick. The thunderstorms, they need 3 ingredients. They need that moist air that has moisture. They need lifting force, something that will push it up, and that can be multiple things. And the third needs to be unstable atmosphere. When the atmosphere is creating conditions where this air will keep accelerating itself. Now, the key word on this slide is normal. If you open up the aviation weather.gov, there is a wind aloft forecast with temperature as of certain periods of the day. You will, well, normally you'd see something about 2 degrees per 1,000 feet, but not always. You can see way less or way more. And that's the first indication of air being stable or not. if you see a higher decrease in temperature, that means that air is unstable. That means that if you adiabatically lift a portion of air, it will find itself in a much colder air at altitude, and the warm object in a cold air will tend to rise more. So now another thing is the temperature inversion. Again, open up the aviationweather.gov. Sometimes you can see a very significant temperature inversion where the temperature is decreasing with altitude increase. We're dropping from 30 at the surface to 28, 26, 24, and then suddenly back to 26 and maybe 30. Typically, it happens when it's colder. But that's another thing to watch for, and I'll have a visual on the next slide. Now, why the temperature, that inversion is an interesting phenomenon, is when the temperature of the air increases with altitude, when you have that layer of inversion, it only does so to a certain point. And at some moment, that atmosphere layer acts as form of a lid, which will keep that weather and pollutants trapped below. And that's probably what maybe was happening. Now, I honestly didn't check, but the last couple days, the whole valley area looked exactly like this. It was pretty clear up above 10,000 feet, but down below 6, it was just bad. Now, let's jump on some visuals. So that concept of me hand waving and pushing the parcel of air, this is a page 107 from Advisory Circular 006B. Hopefully by now, watching me doing this Picasso gesturing, you're motivated enough to go see the real book, which has the real good explanations. It really does. So we have this imaginary parcel of air, something that has a temperature and a dew point. So 18C at the surface and 13C is a dew point. And hopefully from your private pilot days, you remember what the dew point is. And we'll skip explaining that. So what we're looking at, next term is this conversion rate, convergence rate of roughly 2.5 degrees centigrade per 1,000 foot. And this is what's happening. So a 0 at sea level, 1,000 foot, 2,000 feet. The normal, well, in this case, the example we have is the temperature is decreasing 3 degrees per 1,000 foot, so a little higher lapse rate than standard, then 12, then 2 degrees, 2 degrees, 2 degrees. Kind of standard. The dew point will decrease slower than the temperature drops. And the two values, they come together. This column here, that shows you that dew point temperature spread. So down at the ground, in this example, we have 5 degrees centigrade, then 2.5, and then when this dew point spread becomes 0, that's where the clouds form. So today, let's just, out of curiosity, look at the weather forecast in Hillsboro. We have dew point 64 and temperature 88. Unfortunately, there's Celsius, 31 and 17. So if I take a 31, subtract 17, I have 14 degrees centigrade. Now, if I do that simple math, just like in the last line, if I divide 17 by 2.5, I have a 5.6 thousand feet. That's the lowest layer where the clouds are likely to form. Now, it doesn't mean that they will, but if you're looking at the sky and it's typical Oregon winter and there are thick clouds all above you, it's really hard to tell how high they are. You do that simple math, you'll be within a few hundred feet of real base for those clouds. So pretty cool. That's called this conversion. Well, that's how you determine the cloud basis, and that's a convergence rate of 2.5 degrees centigrade. Whew, exhausted. Okay, couple more pictures. Clouds. Now, again, myself, never been expert in clouds, and um, the one on the right, that's probably where you really have to have good understanding what that cumulonimbus is. So that's when a lot of moist air starts to rise up, build this vertical development cloud, and it's super cold up there at altitude. All that moisture is starting to condense, build hail, rain, whatever, and that all falls down when it's ready. So that is a definitely nasty development. Other clouds, low clouds, they're called stratus. I'm trying to think of a strata as an earth, so something close to the earth. And middle is called alta. I probably some Greek or Latin for middle, I guess. And then cirrus, I think of cirrus as R22, flies high, so those higher clouds. So at least I'm trying to say that try to make some sense of the naming, see if you can memorize some names. Now, the types of clouds, I mean, I can't fit so many pictures on a slide. If you dig really deep into those, you understand that there's information that you can distill from the types of clouds that you can see. And the one that more than likely, well, the cumulonimbus definitely, but then lenticular clouds, that's an example that I definitely see a lot asked on various checkrides. Those are, in a few words, they happen in the mountain areas where the air is being forced upslope to clear the mountain. And when it rises so fast because of this mountain lifting force, it starts to become visible moisture. And when it moves downward, it becomes transparent again. And this picture that illustrates how this cloud is not actually right on top of the mountain. It depends on where you look from. But if the wind is coming from the right on this picture, then it rises up here. You see the cloud, and then when it descends, the cloud disappears. The cloud looks like it's just sitting there. In reality, that's an air that's constantly moving through, becoming visible, and then becoming transparent again. Lots of clouds. Okay, something more relevant to our next 6 months of flying. By the way, Alexei, thinking of this weekend, we may have to go IFR on Tillamook. We'll see. You have to think of the plan. So the topic is fog, and think of fog as just a really low cloud. The air always has moisture. Air on the ground is generally warmer, so typically you don't see that moisture, but there are conditions when the fog becomes visible. And to put this simple, the main condition is your dew point spread has to become zero. So either temperature cools or dew point rises, which means the air became more moist. And that's again, on my mock check ride with Sam, he took me back and forth through the fog and how it appears and everything. So that topic I start to enjoy by now. There are 5 key types of the fog: radiation, advection, upslope, steam fog, and ice fog. And I'll go through all them, explaining a little bit more in details. That's what we see in, well, this one, the second picture, advection fog. That's what we see in Tillamook during the day. The moist air comes in from the ocean, it advances, so that's why it's advection. And when it comes in inland, um, the warm, moist air coming into the colder inland then becomes the fog. Again, dew point spread decreases. Radiation fog, similar deal, but that happens more in Hillsborough. That's when the air is just sitting there moist, and we have sunset, and then the earth cools down. Typically by the morning or somewhat like a bit late at night, the dew point spread becomes zero, and then you get radiation fog. It's called radiation because all the heat has radiated away, and now we have conditions to do the fog, to aim to see the fog. Number 3 here, upslope. Kind of like that coastal range. The moist air from the ocean is being blown inland for some other reason, but as it hits the mountains, it's pushing itself upslope where it cools, and when it does, it becomes visible. So that one is self-explanatory. Upslope, you push something upslope, it becomes higher, becomes colder, and becomes a cloud. You have a beautiful video of upslope fog over the coast. I'll try to include that in a video posting later. Steam fog, again, just like it sounds, if the lake is warm enough where it evaporates enough water. It's not boiling, obviously, but it's the same idea as you'd boil a pan of water. It steams and you have the fog. And then ice fog, we don't get that in Oregon, but under certain conditions, when it's that cold and the moisture starts being visible because of the negative temperatures, that would be an ice fog. The term air mass is defining a large bodies of air that is born in a few pretty specific regions on the planet. And think of places like a desert. It's large enough, and the air may stay there for a long time, picking up properties of the environment. And there are two main ways that those air masses are differentiated: by temperature and by moisture. So on the right, I have the cheat sheet. The temperature could be Arctic, which is extremely deep and cold; polar, relatively shallow air mass, and cold or cool or colder; and then tropical. That's something that comes in from obviously tropical reasons and at lower altitudes. Think Ecuador and equator regions, and obviously warm and typically warm, right? Now, and the second is moisture, because both can be either dry or moist under certain conditions. So there is a map of United States, and the arrows, they show you MT, CT. So the way you read that is moist, tropical, or dry, continental, tropical. And when that air mass starts moving, that creates weather for us. Now, when the air mass moves, what happens is a front. The fronts can be warm, cold, stationary, and occluded, and I'll go in details on what they are. But the two main ideas where this all starts is the warm air is a warm front and cold air, cold front, and then there's a weird combination. So how does that work? Warm air, when that warm tropical air, for example, starts moving inland, you'd remember that warm air is lighter than cold air. On top of that, the moist air makes it even more light than the cold. So when Alexei joining, awesome, good timing. Alexei, thanks for joining. Awesome. You can hear us? Check, check.
Yes.
Okay, great. We just started. I'm like on my second slide. We briefly went on describing the air masses as where they born. They differ by temperature and moisture, so they can be either Arctic, which is A, and dry, or they can be coming from the tropical or maritime, M, and T. I'm sorry, maritime or otherwise moist. Either way, that would be a lot of moisture bringing from a tropical lower altitudes, and that's when they have the MT. So that's how the masses get created. When they move, they create fronts, warm, cold, or some combinations. And we just started looking at the warm front. When a warm air mass is moving towards a cold, it is climbing on top because the warm air is lighter, and on top of that, the moist air is even makes the warm air even lighter. So definitely gets on top of the cold air. Now, slowly displacing the cold air away. That's why the warm fronts, they move slow, typically 10, 25 miles per hour. And all that moist air starts climbing on top of the cold, cooling down, and that's when you get a lot of bad weather when the warm front hits. Um, so key properties is bad weather, that moisture gets lifted. You can have various clouds. The closer to the front, the more brutal the weather is. And then, like on this picture they give 600 miles out from the front, you'll have some very light clouds that are starting to appear, but nothing major. Now, the cold front is a different animal. When that Arctic colder air moves inland, you are the front is moving faster, and they can be up to 60 miles an hour, but at least 25, 30. So more than twice the speed of the warm air. What this means is the cold air, again, being heavier, it pushes underneath the warm and creates a lot of lifting of all the moisture that we have. And that's when we have the cumulonimbus clouds. So we have a white front moving through a relatively humid air, create a lot of thunderstorms. Um, Yeah, and so when it passes, obviously weather changes. Cold air brings drier, cold air mass brings drier air, and so cleaner air, cleaner weather. Now, there are two other fronts that you definitely will be in your orals and testings, and that's something to definitely be mindful of. They come up on the pictures on the proc charts. It's often two fronts collide head on. And when they're relatively equal, when the force of both fronts are similar, they can stagnate at a certain place for a while, and that for days. That creates that stationary weather. And the two fronts, they still produce some thunderstorms, some bad weather because the moisture gets lifted, but they they are they have the specific property of staying in one spot for a longer time, and so they will be depicted on the proc charts. The other interesting phenomena is the occluded fronts. That's when the cold front that moves faster catches up to a warm front, which is by definition moves slower, and and that occluded front is making its way through the land. Now, the warm front is ahead of the occluded front, but behind it would be followed by a colder air, colder front than even what has been there in the first place. So we start with a cold-ish air that is being pushed away by the warm front, and then immediately by even colder front behind it. And all that creates a lot of disaster with a lot of moisture being lifted from all fronts. So definitely a lot of rain and other phenomena. Yeah, so that's where we get into the thunderstorms, how they're born, the three stages that you need to know, and the magic number of 20 miles that you need to be away from. Um, you can recognize the thunderstorms by towering nature of the clouds. They're clouds with strong vertical development, and they are three stages: cumulus, mature, and dissipating. Cumulus is when the thunderstorm starts to be being born. The cloud grows. Now it could stop growing and dissipate at any moment, but if we're talking about a full life cycle of the thunderstorm, then it grows into that many mile high towering cloud. And what's going on inside that cloud, that's what creates danger. We are, uh, well, what's going on is we're, Well, we don't have that. But inside the towering cloud, there's a lot of vertical movement. The warm, moist air gets sucked in from the ground and lifted until it cools sufficiently, and that just builds that cloud up further and further. Eventually, at some moment, that um, rising air cannot support the condensation anymore, and when it rains, it pours. It really starts dissipating, and you um, at a higher level of atmosphere, you definitely have hail. When it comes out from the cloud below that, you see there's a line here that shows a 0 degrees Celsius, a freezing line. When it falls down below, it starts to melt. Not necessarily it will melt by the time it reaches the ground, but it definitely can. Now, what happens is the lifting force continues, and hail can be thrown out and outside from the um, thunderstorm for many miles. And the magic number that we have and quote and use is if you're 20 miles away from the cloud, you're safe. But the hail can be thrown up and out from the thunderstorm cloud and carried by the wind. You can easily get hit by the thunderstorm, and that's gonna hurt. Now, how those clouds look. Another descriptive feature is the anvil. The very top of the cloud, when it's rising to that 10 plus mile altitude, the winds at that direction start to displace the top of the cloud. Visually, you can tell which way it's moving. So that thing called an anvil, and that anvil can drop hail onto otherwise cleaner area without the weather. So if you see, like the teaching is, if the pilot sees the cloud with that kind of development, you don't try to pass the cloud in front of its movement. You divert on the opposite side. The clouds move with air. Air can at those altitudes can move to 50 more miles an hour. Definitely passing that kind of development behind it is a good idea. Now, and that's great if it's possible, because there are such a thing as squall lines. So squall lines is a collection of thunderstorms. Like, remember I told you when a front is wide and massive, it can create thunderstorms all along that front line of the moving air, and that line can be very harsh. It could be very difficult to penetrate and nearly impossible to go around. We just looked at the vertical development scale of the clouds. They can be 10 miles high. So for general aviation, definitely not possible to pass over that. For commercial, maybe not as well. Really a one phenomenon that pilots deal with, and that could be a reason for even canceling even a modern commercial flights, because those thunderstorms can be harmful. And specifically there, couple examples. Lighting damage, I've personally never seen this until I came across this picture, but apparently it can burn a hole right through. Must have been very loud on that captain in the left seat. And hail damage can be large and very damaging. Can definitely damage the airframe, can flame out the engines, block the air intake. So a lot of negative consequences possible from the hail. Definitely not fun. Now, moving on into related area, icing. So whenever airplane flies through the area with uh, visible moisture, you can get icing. They differentiate two types of icing, clear and rime, and then the third being a mix of the two. So I guess you can say it's three types, but really the two that possess distinctive characteristics are clear and rime. Clear is when larger droplets freeze and create a clear skating rink kind of experience. And the rime is when you're picking up a lot of air bubbles mixed with the water, and that one is easier to see. Now, there are some airplanes that are approved for flight into non-icing condition. That doesn't mean that it is safe or desirable to stay for any kind of airplane when there's ice building up on the wings. Any airplane will try to get out of icing, and the one question that they'll probably get is, what do you do if on your IFR flight you're picking up ice? It's a tricky question. The first thing that you should do is clarify, is it a little bit of ice, just barely anything, or is it like really half an inch was picked up while you weren't looking? Because if it's severe, you have to declare emergency and do something immediately. If you're just picking up a trace and um, you have safe altitude below you, you can descend and definitely talk to ATC and see what they can offer. But back to a massive ice buildup real quick, kind of like maybe on this picture, you may have nothing else to do but to invoke a 91.3, a pilot um, declaring emergency, because ice buildup ruins the airflow, adds weight, and the airplanes many times have crashed because of unable to fly with ice on the wings. Not fun. Definitely comes up on all kinds of IFR related exams, and that's a hot topic. Now we'll look at a couple charts and tools how you find out about icing. Definitely your friends on interpreting the weather and delivering the weather flight service station. You can get their interpretation of the weather on the ground by calling 1-800-WX-BREATHE, and they are actually amazing. Imagine the people, they look at this weather daily, every minute, not like us only when we prepare for an exam, and they can tell you a lot if the weather is marginal-ish. They are available in the air on multiple frequencies. They're standard like 122.2. There are radio outlets on the VORs, so multiple ways to get hold of them, and they definitely can be helpful, including giving advisories on where the icing is likely and how to avoid that. So that's a useful resource that I believe is underutilized by the general aviation public, in my opinion. Pausing for questions.
Is the ice formed primarily on the leading edge of the wing or other surfaces as well?
Good question. It's definitely primarily starts and grows from the leading edge. The picture on the left could be a little misleading. That would happen if there is a lot of rain that's freezing. Oh, well, yeah, so leading edge, that's definitely where it starts. Now, another important feature,
In flight, I mean, like
it,
when the aircraft is parked, it can, like, freezing rain can fall anywhere.
exactly,
Like,
yeah. In flight, leading edge is where it starts, and especially up above the leading edge. So with a high wing aircraft, it's a little harder to see that because you're looking from below the wings. But another point where it starts building up is any smaller surface. So the smaller the front surface of the area, the sharper that leading edge, the more likely the ice to build up there. So for example, a tail stabilizer, being typically smaller and narrower, will pick up more ice than a fat, larger wing in the front. And that's
okay.
another serious topic, because when you lose your horizontal stabilizer ability to fly, airplane noses down, and not much you can do at that moment.
Is the windscreen likely to collect ice in
It
icing
could,
conditions?
it definitely could, and that's why in PUH you can find one of the actions you take is put on full heat on the windshield so you're not losing the visibility. But probably, well, again, depends on the airplane. In older airplanes, the one item where you can see ice building up the quickest would be the temperature sensor. In many Cessnas, it sticks right through the windshield to the outside. It's a small metal tube, and that will pick up ice before everything else. So find something that is smaller and sticks outside and check that often if you suspect icing is possible. And again, mostly that would be happening when you're flying inside the cloud.
Right.
Okay, good, valid question. Now, next. So FSS, use them. Now, other weather reports, just to starting to kind of summarize on the weather sources. ATIS, AWOS, and ASOS. Took me a while to figure out which one is called minute weather. This one, the AWOS is controlled by FAA, and we have AWOS in McMinnville, in Albany, I believe. You call them even on the phone. It's updated every minute. You can call them on the phone or on the radio. ATIS, for example, is pre-recorded message. For 59 minutes, you get all the same information, and kind of slow to update unless something changes. ASOS, same deal. It's automated. You'll have to memorize it, but this is helpful. So if like right now I'm planning a little flight for the evening, I was checking the weather, and I was calling the AWOS stations to see what's going on in real time. There is a little bit of helpful information there. Now, meters. Hopefully you know how to break those down. You are expected to know that from your private pilot days. Routine weather report. So meters are what's going on there. I would say out of this table, I probably haven't met a person who remembers all of those, but when you look at them often, you typically have a fixed set of what's going on in your flying region, in your flying conditions. Like we don't get snow here, right? We hardly ever get freezing. So we get a lot of baby rain here. Where's the BR? Don't see it. There, mist. Well, the way to remember BR for mist is baby rain. Definitely get fog. We don't get any sand. So the collection of qualifiers and descriptions is somewhat limited. But let me know if we need to stop on this further. I hope this topic is something that you guys as private pilots are comfortable with. And okay, good. Now, forecasts, similar deal. TAF, terminal aerodrome forecasts, they're given for area of about 5 miles radius, and typically valid for at least 24 hours with subdivision inside that region. So they would give a larger forecast, like overall what's expected, and then within that they would have a from such time you expect this forecast. You can read that literally from the front outward. If it says like from today, like 5 p.m. today until 5 p.m. tomorrow, expect overcast 3,000, but the next line says from 6 p.m. today, you expect overcast 5,000. Well, great. So there's your indication that it will be changing. What else? Oh yeah, Zulu time. So the forecasts are updated at 0, at 6, 12, and 18 Zulu 4 times a day. So when you're looking for a new forecast, just check those 11 a.m., 5 p.m. times when you get the new forecast dropped. Ceiling or not? That is a tricky question. And hopefully this, yeah, Alexei, question?
What about MOS?
MOS.
Yeah.
It's a weather. You know what?
It's I don't think it's like official FAA weather, but it's computer assisted or generated or whatever. But I've been using it. It gives pretty good results.
Yeah, okay, good one. You caught me off guard. I like it. Thank you.
Cool.
Okay.
Yay.
This one. Memorize that if more than half of the sky is covered, that counts as a ceiling, because you will get questions looking at random meter, what's the ceiling? And then if you see few or scattered, that's not a ceiling. Sky clear, obviously not a ceiling as well. So there's something to remember. PIREPs, often called as the most accurate report on the information, because in a specific point in space and time, they would give you a very detailed report. And unless they're wrong, which happens, then this is your best weather on trusting that person. So there's a lot to distill in. They can be quite complicated, but at least the things that would be reported is normally ceilings, top and bottom, because with ground weather reporting, they can't report the top of the clouds, not in real time at least. And turbulence, wind shear, freezing levels, anything that could be of interest or help, it's generally very helpful and considered to be a very good practice to throw in a report or two when the weather is of interest.
I think PIREPs can be a little bit subjective. For example,
Yes.
Turbulence, right?
Oh yeah.
Light turbulence for Airbus is probably pretty big turbulence for Cessna. So
Exactly.
you should
Which
consider those.
Which is why it always includes this type, the TP C-182. That's a type of aircraft, Cessna 182. And if Cessna is saying it's heavy turbulence, it may be actually nothing burger. But if it's a 737 moderate turbulence, that's a problem.
Stay away.
So yeah, definitely pay attention what kind of airplane is that. What else? Air mets. There are 3 air mets. Now, one thing about air mets they are advisories. Every 6 hours with updates as needed. And that's just defined as operational interest to all aircraft. Definitely more, like you just mentioned, more severe impact on a small aircraft, turbulence. Definitely smaller aircraft get beaten up more. But in general, this is applicable to all aircraft. So AirMet, just that meteorological observations or advisories. Now, SIGMETs, just like the name suggests, is something that's significant. And there are what we have 4 main significant categories: icing, extreme turbulence, and again, significant, there are specific metrics, and I may get this wrong, but I think ice has to be moderate or severe, and turbulence, again, somewhat subjective, but has to be severe or extreme, or clear air turbulence when it's not expected. Dust storms, sandstorms, something we don't have with low visibility, and volcanic ash. The SIGMETs are not scheduled. They are popped up if weather is forecasted. So that's the key thing, is that's an advisory on the forecast. And they're valid for 4 hours. And I believe the convective SIGMETs are only valid for 2 hours, because convective activity just so quick to change, it's hard to keep it valid for much longer. So again, this is an overview. But the areas to know, to pay attention to, is there's what's AirMet, what's SIGMET, what kind of information that is, and specifically SIGMETs being a forecast, and how often to expect that, how long is it valid. Those are all the numbers that typically get asked. Luckily, they're all either 2, 4, or 6, so pretty easy to remember. Definitely, ForeFlight is doing a great job on visualizing all those. I can't imagine how difficult it was to disseminate all those segments in textual form. When you look at the map and below example, and it just shows the graphical area, well, that's great. Nothing in Oregon on this map. What else? More weather reports. Winds, big deal. They definitely change with altitudes. There's pretty complicated, sophisticated way that the winds aloft are built. There aren't that many points where the information is collected, and the rest is extrapolated. So the windy app, for example, I believe it's just doing a lot of extrapolation or interpolation, whatever. Some just guesstimating the data. Those forecasts are only twice a day kind of information, and they send zones. They send those spy balloons up in the air to pick up that information. So it's pretty labor-intensive process. The way to read the tables, this will definitely come up. The wind is given by two numbers for direction and then two numbers for the wind speed, the negative temperature or a positive temperature, and then the temperature itself. Now, the plus minus sign is only shown up to 24,000 feet. From a 30 onward, they decided to save a space, character space. There's no sign because it's always negative. And one example down below here, when the direction is in the 70s or 60s, that means that the wind is stronger than 99 knots. So you have to add 100 to the wind. In this case, it's 106 knots wind, and subtract 50 from the direction. So direction would be 23, and the wind speed would be 106. So there's a little bit of coding going on, and that's how they built the system decades ago. That's still how we use it. Couple other slides. Surface analysis chart. That tells you the areas of high and low pressure. That depicts the fronts. See the cold fronts with a blue triangle, the pieces of warm front with the red, and this one is a bit of a stationary front. It looks like a mix. At least this portion is stationary. Often this would have a legend down below if you look, but on the test often there is not. So the ways that they picture the fronts definitely worth memorizing. And again, all of that is in the advisory 006B. It's pretty interesting, awesome read. Low-level probe charts. Another forecast of aviation weather covers, well, for US, covers all the 48 states, and they're typically 12-hour forecast and 24-hour forecast. So more precise and or more longer term. Issued 4 times daily. Again, often asked, and this is helpful to remember if you're looking for a fresher one, you know what to expect. And the things to look on this forecast is the trout area, the areas of the lower pressure, for example, and the low pressure means that air is rising. When it rises, it creates bad weather, clouds and rain. So low pressure areas are just that. Look at the higher pressure areas, typically better weather. So this is where this weather evaluation would start, by looking at the bigger map with bigger cyclones. If you're planning a cross-country trip, this would give you a good guess on the wind direction. You want to fly above the high area, and below the low if you're flying from west to east. And is who knows why? Or I realize I may not have a slide of how actually we did that last time. Give me a hand or something. Is what I just said, that if you take a high pressure area, this one, and if you're flying west from California, from west to east, you would pass this above or north of the area. Why is that?
North, because the winds are clockwise for high pressure areas, counterclockwise for low pressure areas in the northern hemisphere.
Exactly. Oh, yeah. It's all focused on the US. Thanks, Alexi. Yeah, I just want to make sure I didn't lose you, at least not all. So yeah, that's where it starts. And then looking at low pressure areas above, that would be counterclockwise. So if you go kind of mid Oregon and to the east, at least for the initial while, you're expecting to have more tailwinds. good stuff. If you go the other direction, that could be a different route. What else? Icing. There are multiple icing products, and it starts with looking at freezing levels, at temperatures. If it's 10 degrees on the ground, icing is likely to start at 5,000 feet, so it's simple as that. But then icing takes more than just the temperature. So there are icing charts that would forecast the type of icing, and probably if you fly just around Portland, Oregon, Hillsborough here somewhere, we don't use those kind of products. We just look at the clouds and the temperature if you go instrument. But if you're doing a cross-country flight, this is where you'd get into using the icing forecasts and charts. And look at me, I made it to the end. I do have a quiz link that I can send, and we can just chat on the weather, see if any questions, how much you guys made this. Ryan, I haven't heard from you lately. How are you pushing along? So let's just connect. I'll stop the recording so we don't feel shy to share. Try to